Okay, in this video we're going to take a look at the equations of motion that we're going to use in rotation. And like I said earlier, most of our equations, they're just crossovers. The only thing we have to do is change what the variable looks like so that we know that we're looking at a rotational quantity instead of a translational quantity. And because we draw our vectors in the exact same manner that we drew the vectors for translation, it turns out that pretty much everything we do is identical when it comes to graphical analysis and computations. So let's go ahead and start by just laying out a comparison for the various equations that we use. Now, you know that in translation, we have four basic equations that we tend to resort to. The first one is the position function, and we just write d is equal to v initial t plus 1/2 at squared. In rotation, it looks identical to that, but with the rotational variables. So, for example, instead of d, we write delta theta because that's angular displacement. V initial becomes omega initial t, and then the acceleration is going to be alpha t squared. Okay, so the equation looks exactly identical. Then we have the acceleration independent equation, where d is equal to 1/2 times v initial plus v final times t. And in rotation, we write delta theta is equal to 1/2 times omega initial plus omega final times t. The time independent equation, v final squared equals v initial squared plus 2ad. And so in rotation, it becomes omega final squared is equal to omega initial squared plus 2 alpha delta theta. And then lastly, let's not forget the velocity function, which is really just the definition for acceleration. And so we have v final is equal to v initial plus at, or you may see it written as a is equal to v final minus v initial over t. And so in rotation, that's going to become omega final is equal to omega initial plus alpha t. So you can see that there's really not any difference in how the calculations work. Now, the one thing you just want to keep in mind is that all of these equations are only valid if the acceleration is constant. So the acceleration must be constant. If the acceleration is not constant, then you're going to get an answer which diverges from the real answer. So depending on what those differences are, you could end up with a radically different answer or something that looks close and makes you unsure of your answer. So just be certain that it's constant acceleration. And of course, alpha, a constant alpha would be in order here as well. Okay, so let's take a look now and just review a little bit of our graphing techniques, just some of our basic properties, because graphing is going to be just as valid and just as important in rotation as it was for translation. It's going to be a way of dealing with acceleration that isn't constant, for example. Okay, so remember that when we draw our graphs, that typically our graphs are going to be going from position, then we want to put velocity underneath it, and then acceleration underneath that. And so before it was position versus time with an x, now it becomes theta versus time. It becomes omega versus time, and then it becomes alpha versus time. So angular position, angular velocity, angular acceleration. All right, now the properties of the position time graph. Remember that the slope is going to indicate the velocity, If it is a straight line, there's going to be 0 acceleration, or in this case, angular acceleration, which is the letter alpha. If it is a curved line, then that's going to be equal to a constant acceleration. In fact, the curved line has to be specifically a parabola. So this would indicate right here that we have a constant acceleration. Okay, the area of the position time graph is nothing. It is not physically meaningful. Now on the velocity time graph, it may look something like this. And on the velocity time graph, we have the slope is going to be equal to the acceleration. And then we have the area is going to be equal to the displacement. Now remember, this is angular displacement, so this is going to be delta theta. Remember also that unless you are given the initial position, you cannot find the position using the area only. And that the area is represented, or represents the area between the x-axis and your line or your curve. So that represents the area there. Finally, we get to the acceleration time graph. And on the acceleration time graph, the slope we will not look at, but the slope would be considered the jerk. No need to think of it beyond this video. I don't even know if I would write it down if I were you, because you're going to study it and for no good reason. Okay? But the slope is equal to the jerk, and the area is going to be equal to the change in velocity, which is delta omega in angular variables. And so the area for an acceleration time graph is going to be either, well, it doesn't have to be a horizontal line, but if it's constant acceleration as I have here, then it's going to be a horizontal line. And the area is going to be represented by this. And if it happened to be a negative acceleration, then the area would be represented by this. Okay, now I do want to point out before I finish this video that this position time graph that I've drawn here does not coincide with what I've drawn here. Okay, the velocity starts out as a negative velocity, and my position time graph has a positive slope continuously. So this graph that I've drawn for the position time graph only corresponds to this point in time and beyond. Okay, so this graph does not fully correspond to this one.